Have they ever looked up at the night sky and wondered whether the universe is hiding something even older than the story science has told for decades? Because the James Webb Space Telescope is now seeing galaxies, black holes, and chemical signatures so early, so massive, and so mature that they seem to defy the timeline of the Big Bang itself. What Webb is finding does not simply challenge a few small details. It raises a far deeper possibility that something in the early universe is missing from modern physics, or that the universe begins in a way no one fully understands yet. Before beginning, please take a moment to like the video, subscribe to the channel, and share it with someone who loves cosmic mysteries and the unknown. Thank you so much for being here and for spending time with this journey into the deepest questions in the universe. And, if they would like, it would be wonderful to know what time it is where they are listening from and where in the world they are tonight. Now, with that said, let us step into one of the strangest discoveries of the modern age and begin. A patch of sky the size of a grain of sand held at arm's length does not look like the place where a crisis should begin. It looks too small, too ordinary, too easy to dismiss. Yet that is where the James Webb Space Telescope points when it begins to send back its first full-colour images in July of 2022. The target lies behind the galaxy cluster known as SMACS 0723, a region already familiar to astronomers because gravity there bends light and reveals objects that would otherwise remain hidden. The image arrives from a telescope floating near the second Lagrange point, almost 1 million miles from Earth, sheltered behind a sunshield the size of a tennis court, and staring into infrared light with a mirror of gold-coated segments, aligned to astonishing precision. It is the most powerful observatory ever built for this purpose. It is designed to look backward through time, into the long red stretch of cosmic history, toward the first stars and the first galaxies. For years the expectation has been clear. It will show dim beginnings, it will show rough drafts, it will show the universe while it is still learning how to build. Instead, it seems to show the opposite. At first, the image inspires the usual response. Awe comes first, because the field is crowded with thousands of galaxies, each one a separate island of stars, each one carrying light that began its journey billions of years ago. Some are twisted by lensing into long arcs of light, some appear as pale smudges. Some are so distant that their glow has shifted out of visible wavelengths and into the infrared, where the James Webb Space Telescope is strongest. The photograph feels like a triumph of engineering and patience. It is exactly the kind of image the mission is supposed to produce. But within hours of release, astronomers around the world begin downloading the raw data and running their own analyses, and in that quiet second stage the mood changes. Tiny red points buried in the field begin to stand out. They are too bright for their presumed age. They seem too compact and too developed. If their distances are what they appear to be, then they are shining from a time when the universe is only a few 100 million years old. That should make them primitive. They do not look primitive. Cosmology enters this moment with a very orderly story already in place. After the Big Bang, the universe expands and cools. In the first few minutes, only the lightest elements form in significant amounts, mostly hydrogen and helium. Then comes a long, dark interval. Matter is present, gravity is at work, but stars have not yet switched on. Eventually, small overdensities in the invisible scaffolding of dark matter draw gas inward. The first stars ignite. Small proto-galaxies appear. Over immense spans of time they merge, feed, brighten, and grow. This is called hierarchical growth. It is the slow architecture of the Standard Model. Small things come first, large things come later. Complexity takes time, maturity takes even longer. The earliest galaxies are expected to be faint clumps with modest masses and simple chemistry, not because anyone prefers that picture, but because the clock seems to allow little else. The first Webb image does not yet destroy that clock, but it makes the ticking sound uncertain. This matters because the observatory has not reached these depths by accident. The telescope is built for exactly this territory. It launches on Christmas Day in 2021 aboard an Ariane rocket from French Guiana. After the long unfolding of mirrors and shield and the careful months of calibration, each instrument comes online to do a different part of the work. One camera maps near infrared light. One spectrograph can split that light into its component colours and read the fingerprints of atoms within it. Another instrument reaches deeper into mid-infrared wavelengths, where ancient stretched light becomes visible again. The entire machine exists to solve one problem: how the first luminous structures emerge from the dark. It is supposed to confirm decades of theory with sharper detail. Instead, it begins by raising the possibility that the theory has left something out. The first anomalies are easy to resist. Every new telescope surprises its operators. Early data often carries calibration problems. Brightness can be misread. Distances can be overestimated. Strange colours can mimic great age when dust or unusual stellar populations are involved. Astronomers know this and react with caution. They tag the suspicious objects, estimate their redshifts, compare independent pipelines, and wait for stronger evidence. In this stage, the field behaves exactly as it should. Nobody serious rushes to overthrow cosmology because of a handful of bright smudges in a brand new image. But the strange objects do not disappear as more data arrives. They multiply. Other deep fields show the same pattern. Wider surveys, built from different patches of sky and handled by different teams, begin finding similar sources. Again and again, the early universe appears to contain galaxies that are brighter, denser, and apparently more massive than the standard story comfortably permits. The tension is easiest to feel through scale. A mature galaxy is not a simple thing. It requires gas to collapse into stars. It requires stars to live long enough to alter their surroundings. It requires repeated cycles of formation, radiation, explosion, and enrichment. Even a modest galaxy is the result of layered history. Yet the objects emerging from the first Webb fields seem to carry that layered history almost immediately. They look less like the first rough shelters in a new landscape, and more like finished cities glimpsed through fog. The comparison that spreads quietly through the community is blunt for a reason. It feels like pouring a foundation one evening and waking the next morning to find a furnished mansion where wet concrete should still be drying. What makes the moment so unsettling is not simply that the objects are there, but that they appear in the exact observational regime where the standard model ought to be strongest. The broad framework called lambda cold dark matter has explained much of the large-scale universe with remarkable success. It describes a cosmos made mostly of invisible components, dark matter and dark energy, with ordinary matter contributing only a small fraction. It reproduces the texture of the cosmic microwave background. It traces the growth of structure across billions of years. It has earned its authority. Yet in the first few 100 million years, where the James Webb Space Telescope now sees farther and more clearly than anything before it, the expected sequence of events begins to look rushed, almost skipped. The early galaxies do not merely arrive early. Some seem to arrive already advanced. That distinction changes the atmosphere. A slightly earlier galaxy would be a puzzle. A chemically mature, unexpectedly luminous, compact object at extreme distance is something else. It hints that the difficulty may not be a missing detail, but a missing stage. Perhaps stars form faster in the early universe than expected. Perhaps the first stellar populations are heavier and brighter than modern ones. Perhaps black holes grow before galaxies do. Perhaps some of the sources are not galaxies at all. At this point, none of those possibilities is proven. What is proven is simpler and more troubling. The light is real. The pattern repeats. The first glimpse into cosmic dawn does not show a beginning that is gently unfolding. It shows a universe that seems to have started before the official story says it had time to begin. The image from that grain-sized patch of sky therefore does something unusual. It does not merely extend vision, it changes the meaning of distance. Every faint red source in the field is now more than a remote object. It is a test of the timeline itself. The farther the telescope looks, the less empty the beginning appears. The dark ages begin to look crowded. The first few 100 million years begin to look busy, structured, and strangely experienced. The James Webb Space Telescope is supposed to reveal the first chapter of visible cosmic history. Instead, in its opening act, it seems to uncover pages that already look halfway read. The first response to an impossible result is almost never belief. It is measurement. It is repetition. It is the slow effort to find out whether the surprise comes from nature or from the machinery built to observe it. That is what follows the first wave of James Webb discoveries. The strange objects from the earlier surveys do not immediately become evidence that cosmology is broken. They become files to be reopened, brightness values to be rechecked, distance estimates to be challenged, and assumptions to be stripped away one by one. This is where the real pressure begins, not in the first headlines, but in the months after, when the field does what it is supposed to do and the anomaly remains standing anyway. The standard picture is still simple enough to state plainly: the universe begins hot, smooth, and almost chemically empty. Tiny fluctuations in density become the seeds of everything that follows. Dark matter gathers first because it does not interact with light and can begin clumping early. Ordinary gas falls into those invisible wells. Small clouds cool, fragment, and light up as stars. The first galaxies are expected to be compact and faint, with low mass and little internal complexity. Later, through merger after merger, larger galaxies emerge. The pace is not arbitrary. It is set by gravity, cooling, radiation, feedback, and time. Time matters more than anything else. There is only so much structure that can be built in a few 100 million years. There's only so much gas that can become stars before the stars themselves begin fighting back, heating and blowing away the raw material around them. So when early Webb fields begin showing objects at redshifts above 7, above 10, even near 14, the problem is not just that they are there. The problem is how complete they look for their age. Several major survey programs push this issue forward. The deepest observations from the James Webb Advanced Deep Extragalactic Survey search for the faintest and farthest sources. The Cosmic Evolution Early Release Science Survey covers a wider field and finds more statistically troubling examples. Broader mapping efforts such as Cosmos Web add another kind of pressure by showing that the phenomenon is not confined to one unusually strange patch of sky. Different teams, using different methods, keep recovering the same broad impression. The early universe appears too bright, its galaxies appear too abundant, their inferred masses often land too high. At first, those masses are derived from photometry alone, which means they come from how bright an object looks across different filters, rather than from a full spectrum that can pin down its distance with far greater confidence. This is important because photometric redshift is powerful but indirect. It reads the overall color pattern of an object and infers how much the universe has stretched its light. In the nearby universe, this works well. At the frontier, where the first galaxies are dim, unfamiliar, and seen only through a few bands of light, uncertainty grows. A dusty object at lower distance can sometimes mimic the colours of an object at great distance. An unusual population of stars can distort the estimate further. Every experienced observer knows this. So the early claims are treated as provisional. Still, the provisional claims are dramatic enough to force attention. Several galaxies in the early survey data seem to carry stellar masses in the range of billions, or even tens of billions of solar masses when the universe is only a few 100 million years old. That scale is what makes the problem difficult to dismiss. A galaxy does not acquire such mass by accident. Stars have to form, gas has to cool and collapse. The first generation has to ignite, radiate, alter its surroundings, and in some cases die. The suggestion that large, mature-looking galaxies are already present so early feels less like a mild discrepancy and more like an accounting problem. There simply does not seem to be enough time in the cosmic budget for the work to have been completed. Theoretical cosmologists begin stress testing the standard model against these observations. One of the most widely discussed analyses asks a very direct question. If the early mass estimates are taken seriously, does the known supply of ordinary matter in the universe at those epochs even permit such galaxies to exist in the reported numbers? The answer comes back uncomfortably close to no. In some cases, the implied stellar mass density appears so high that it threatens to overdraw the baryonic budget itself, meaning that the stars already formed in these systems would represent too much of the ordinary matter that should be available that early. This is where the phrase impossible galaxies begins to spread. It is a memorable label, but it also obscures the real issue. The problem is not that the Big Bang has failed. The expansion of the universe, the cosmic microwave background, the basic early history of matter and light remain intact. What is in question is the route from that beginning to the galaxies Webb appears to be seeing. The trouble lies in the timeline between the opening event and the mature structures already shining not long after. Then the corrections begin. This is the stage that usually calms a scientific panic. Instrument calibration improves. The early photometric pipelines are refined. Fluxes in some wavelength bands are adjusted. Objects once thought to sit at extreme redshift are found to be somewhat closer. Masses come down, in some cases sharply. Spectroscopy arrives and does what spectroscopy always does. It narrows the argument. A full spectrum can reveal emission and absorption features tied to specific atoms and, through them, far more secure distances. Some early candidates move down the ladder. Some survive at high redshift but with lower estimated masses. The loudest version of the crisis softens. For many outside the field, that seems like the end of the story. The telescope surprised astronomers. Astronomers corrected themselves, and the universe returned to normal. But that is not what actually happens. The key detail is that the corrections reduce the tension without removing it. The numbers become less theatrical, yet the underlying mismatch survives. A galaxy that falls from 10 billion solar masses to 1 billion solar masses at extreme redshift is no longer headline material in the same way, but it is still difficult to explain under ordinary assumptions. The crisis changes shape. It becomes less photogenic and more persistent. That is often the more dangerous kind. A dramatic anomaly attracts scrutiny and counter-arguments. A quieter anomaly risks being treated as resolved simply because it is no longer sensational. Yet in the background, the models are still coming up short. Proposed fixes appear one by one. Perhaps the first generations of stars are unusually top-heavy, meaning they contain many more massive stars than stellar populations in the modern universe. Massive stars are far brighter per unit mass, so a galaxy can appear heavier than it really is if it is dominated by these luminous short-lived giants. This is a legitimate possibility, and later simulations show that it can lower some inferred masses by a factor of several, even close to an order of magnitude under generous assumptions. But even this does not fully erase the issue. A reduction is not the same as a reconciliation. Many of the early objects remain at or beyond the edge of what hierarchical growth models comfortably allow. This creates an awkward pattern. Every correction seems to say the same thing. The first claims are too strong, but not wrong enough. The revised data no longer demands abandonment of the standard model in a single dramatic gesture, yet it keeps demanding exceptions, adjustments, and special early conditions. That is where the sense of strain deepens. A strong model can survive surprises, it can survive even serious ones. But when the same early epoch repeatedly produces objects that need to be explained away as unusually bright, unusually efficient, unusually heavy, unusually chemically evolved, or unusually misclassified, then the weight of the word unusual begins to accumulate, by itself that may not overturn a theory. Together those repeated exemptions begin to look like clues. The surveys keep expanding. The sample grows. The universe at early times refuses to thin out into the simple nursery the old picture anticipated. It looks crowded with overachievers. It looks active, fast, and in some places alarmingly mature. The corrections matter. They are real, necessary, and scientifically healthy. Yet their deeper effect is almost paradoxical. They do not close the case. They make the surviving residue harder to ignore. What remains after every adjustment is a timeline that still feels compressed past comfort, a sequence of growth that still appears rushed, and a suspicion that the early universe is not merely forming galaxies faster than expected. It may be following more than one pathway at once, with some of those pathways absent from the standard script entirely. By the time the mass estimates are revised and the first wave of disbelief settles into a quieter unease, the mystery has already moved to a deeper level. The question is no longer only how heavy the earliest galaxies are. It becomes how they're doing what they appear to be doing at all. This is the point where the light from the first billion years stops looking like a bookkeeping problem and starts looking like a problem in physics. The galaxies are not simply present too early. Some of them seem to be making stars with an efficiency that modern astrophysics does not know how to permit. In the nearby universe, star formation is not especially neat or especially generous. Gas clouds collapse under gravity, but only part of that gas ends up in stars. The rest is pushed back, heated, blown apart, or stirred into turbulence by the very stars that have just formed. This is called feedback. It is one of the quiet regulators of the cosmos. A newborn massive star floods its surroundings with radiation. Stellar winds carve cavities into the cloud. Then, after only a few million years, the most massive stars explode as supernovae and hurl material outward with enough violence to disrupt further collapse. The process is self-limiting. Gravity begins the work, but the stars answer back. In ordinary galaxies, this gives star formation a kind of brake pedal. Only a fraction of the available gas is turned into stars in any given episode. The number is not exactly the same everywhere, but across a vast range of galactic environments it tends to stay modest. Nature appears reluctant to let too much gas become starlight too quickly. That is why the early objects found by the James Webb Space Telescope feel so strange. Some of the most discussed examples are intensely blue in the ultraviolet part of their spectra. Once that light is reconstructed from the infrared observations, blue, in this context, does not mean calm or decorative. It means young, hot, vigorous star formation dominated by massive stars that burn bright and die fast. These systems are compact, often astonishingly compact, yet they produce a level of ultraviolet light that suggests starbirth on a scale out of proportion with their size. They are sometimes described as blue monsters, not because they are large in physical extent, but because their light output is difficult to reconcile with the amount of gas and time apparently available to them. Some are only a few hundred light-years across. That is tiny on a galactic scale. The Milky Way spans roughly 100,000 light-years, yet these small systems appear to hold stellar masses ranging from tens of millions to hundreds of millions, and in some interpretations around 1 billion solar masses, packed into such tight volumes and seen at epochs only a few 100 million years after the Big Bang. They imply star formation that is both extremely rapid and unusually effective. To understand why this matters, it helps to picture what the standard models assume about the first galaxies. They're expected to be fragile things, low mass, metal poor, bursty perhaps, but not overwhelmingly efficient. The first stars are thought to form out of nearly pristine hydrogen and helium gas. Without heavy elements, cooling is less efficient and gas behaves differently. There are reasons to think the first stellar populations might be unusual, perhaps skewed toward more massive stars than modern ones. Even so, the basic feedback problem should remain. Once stars ignite, they should begin disrupting the very process that made them. This is not an optional detail. It is built into the known behavior of gas, radiation, and gravity. Yet the observations imply that in some early systems the brake has been weakened, bypassed, or overwhelmed. Some analyses suggest star formation efficiencies above half of the available gas supply. In a few of the earliest interpretations, the numbers drift toward the unsettling idea that nearly all the gas in a region is turning into stars. That does not merely stretch the usual assumptions, it approaches the edge of what current physical understanding considers plausible. The puzzle is not that gas can form stars. The puzzle is why the ordinary self-regulation seems so ineffective in these conditions. Several explanations are explored. One possibility is that the dense environment of the early universe somehow changes the balance. Perhaps gas streams into these systems more continuously, replenishing fuel faster than feedback can expel it. Perhaps the dark matter wells are compact and deep enough to hold on to gas despite the blast of newborn starlight. Perhaps the earlier stellar populations are so different that the light-to-mass ratios are misleading, causing these systems to appear more productive than they really are. Or perhaps the structure of the gas is unlike that of later galaxies, allowing collapse to proceed in a more coherent way before turbulence and radiation have time to intervene. Each of these ideas captures part of the difficulty, but none has become a full explanation. The deeper problem is that the Webb observations do not reveal just one class of exaggerated system. They reveal variety. Some early galaxies appear compact and almost hyperactive. Others at similar redshifts seem more extended. Some show signs of strong emission from gas excited by young stars. Others hint at more complicated internal structure. The early universe is not simply producing one bizarre object over and over. It seems to be producing multiple kinds of advanced objects very quickly, which suggests that if some unknown process is operating, it may not be a single trick. It may be a broader change in the rules of early growth. This becomes even more uncomfortable when the blue systems are placed beside the revised but still substantial galaxy masses discussed earlier. A top-heavy population of massive stars can help explain brightness. It reduces the amount of total stellar mass needed to produce the observed light. But that move carries its own price. Massive stars are short-lived and violent. They enhance the very feedback that should suppress runaway formation. The same adjustment that helps with the mass problem can worsen the mechanism problem. A galaxy made of many hot, massive stars should be even more aggressive in pushing gas outward, not less. So a proposed rescue in one corner of the puzzle opens tension in another. The pattern repeats. The universe seems to demand one exception after another, but the exceptions do not always cooperate with one another. That is how the mystery deepens. It stops looking like an observational misunderstanding and starts looking like a system with too many symptoms to be explained by one simple error. The compactness of these early galaxies adds another layer. In modern galaxies, star-forming regions can be fierce, but the whole structure is large enough to spread processes out over vast distances and timescales. In the early objects, everything seems crowded together. Stars form in small volumes at high density, with light pouring out from systems that resemble galactic cores more than ordinary young galaxies. The density itself becomes part of the riddle. Densities that high may enable fast collapse. They may also intensify collisions, radiation fields, and gravitational interactions. The result could be a mode of star formation that has no good nearby analogue. This is one of the reasons the first Webb galaxies often feel so difficult to interpret. They are not simply younger versions of things already familiar. They may belong to regimes of astrophysics that no local object can properly teach. What is known remains important. The light is measured. The compactness is inferred from the shapes and sizes Webb resolves. The ultraviolet slopes indicate very young and intense stellar populations. The broad conclusion that at least some of these systems are converting gas into stars with startling speed is difficult to avoid. What remains unknown is why. When a phenomenon appears again and again but the usual regulating forces seem absent or reduced, speculation begins to widen carefully. Maybe the earliest gas clouds fragment less than expected. Maybe the first stars form in short, overwhelming collapses before feedback can fully switch on. Maybe some of the light is not starlight in the ordinary sense at all. Maybe embedded black holes, accretion processes, or exotic transient phases contribute to what is being interpreted as pure stellar output. That last possibility becomes more interesting later, but even here the seed is present. The early universe may not merely be making stars too well. It may be producing luminous structures that are being named galaxies, because the catalogue of alternatives is still too small. This is where the emotional tone of the evidence changes. A mass discrepancy can feel technical. A problem with star formation efficiency feels more intimate because it touches the engine itself. It suggests that the first visible structures in the universe are not simply arriving ahead of schedule. They are operating by rhythms that current theory does not comfortably capture. The stars are too eager. The feedback is too weak or too late. The gas is behaving as though some hidden condition in the first few 100 million years favors construction over restraint. The standard story says the universe should still be hesitant, rough, and incomplete. Webb keeps finding systems that behave as if hesitation has already ended. They burn blue, they form fast, they condense extraordinary amounts of activity into tiny spaces, and as soon as that behavior is accepted as real, another question begins to rise behind it. If the first galaxies are making stars this aggressively, then they should also be changing their chemistry far sooner than anyone expected. The light should not only be bright, it should begin carrying the fingerprints of a universe growing old too quickly. Light from the early universe does more than announce that something is there. When spread into a spectrum, it begins to reveal what that something has already done. This is where the mystery sharpens again, because brightness alone can still leave room for reinterpretation. A source may be closer than first thought. Its stars may be heavier than assumed. Its mass may drop as calibration improves. Chemistry is harder to move aside. A spectral line from oxygen or nitrogen is not merely a sign of luminosity. It is a record of time already spent. It tells a story about stars having lived, burned, and changed their surroundings. It tells a story about generations, not beginnings. That is why the chemical detections from the James Webb Space Telescope feel so disruptive. They do not simply suggest that early galaxies are bright. They suggest that some of them are already old in the only sense that matters to astrophysics. They have processed raw cosmic matter into something more mature. They have already altered the universe around them. In the first minutes after the Big Bang, the universe produces mostly hydrogen and helium. with only traces of a few other very light elements. That primordial mix is simple by design. All the heavier elements come later, built inside stars through nuclear fusion, and then thrown back into space when stars shed their outer layers or explode. Oxygen is born in the hearts of massive stars. Nitrogen often requires a more extended cycle, involving stars that live longer and die more gently. Carbon-rich molecules demand further processing still. This is why cosmic chemistry is so deeply tied to time. Before stars, there are no heavy elements in meaningful abundance. After the first stars, there are some. After multiple generations, there are many. A chemically mature galaxy is therefore not just a bright object. It is a place where history has already accumulated. The James Webb Space Telescope begins finding signs of that accumulation at moments when the universe should barely be waking up. One of the most striking cases comes from a galaxy whose light began its journey when the universe is only about 290 million years old. The object is exceptionally distant, and its spectrum becomes famous not simply because of its record-setting redshift, but because buried in that spectrum is evidence for oxygen. Oxygen should not be impossible at that age. It is not forbidden. Massive stars can live fast and die in only a few million years. In principle, if the first stars form very early, and if star formation proceeds with unusual speed, then oxygen can appear relatively quickly. But the margin is razor thin. Gas has to collapse. Stars have to ignite. The first generation has to live long enough to fuse heavy elements and die violently enough to return them to surrounding gas. Then the enriched gas has to participate in a new luminous system whose signal can be detected across more than 13 billion years of space and time. Every step is possible. The combined schedule is what makes the result unsettling. It compresses the normal sequence almost to breaking. This is the kind of observation that does not overthrow a theory by itself. Instead, it makes the theory feel breathless. It pushes every stage to its earliest and fastest conceivable limit, and then asks whether even that is enough. Perhaps it is, but only if many favourable assumptions all happen to align at once. That is where mystery begins to grow. The early universe keeps requiring best-case scenarios merely to appear ordinary. Then nitrogen enters the story and the pressure increases. In another famous early galaxy, observed at a somewhat later but still astonishingly young epoch, spectral analysis suggests a nitrogen abundance relative to oxygen that is difficult to explain by standard chemical evolution. Nitrogen is a more patient element. In the usual picture, it builds up through stars of intermediate mass that live far longer than the massive stars responsible for rapid oxygen enrichment. Those stars need time to age, swell, and release their processed material back into space. The process is not immediate. It unfolds over many tens to hundreds of millions of years, and a strong nitrogen signature therefore tends to imply a more developed stellar history. Yet this galaxy appears to carry a nitrogen to oxygen pattern that feels more like the chemistry of a system with far more elapsed time behind it. The usual route to such enrichment seems too slow. Again, theorists search for ways around the difficulty. Perhaps there are supermassive stars in dense early clusters, objects far heavier than normal stars, born through repeated collisions in packed environments. Such stars could process gas rapidly and enrich their surroundings on very short timescales. It is a serious idea, but also a revealing one. The data is now forcing astrophysics to lean on categories of objects that remain largely theoretical, not because the theory has directly predicted them in abundance, but because the observations seem to demand something faster than familiar stellar evolution can comfortably provide. The problem broadens further when the chemistry stops being only about isolated elements and begins involving complex carbon-based molecules. Polycyclic aromatic hydrocarbons are long-named but conceptually simple, flat-ringed structures built from carbon and hydrogen. common in modern interstellar space and usually associated with evolved stellar populations and chemically processed environments. They are not the sort of thing expected to appear casually in the youth of the cosmos. Their presence implies carbon production, transport, survival, and accumulation. It implies stars that have moved well beyond the earliest phases of cosmic life. Yet James Webb detects signatures consistent with such molecules in a galaxy from within the first billion years. This is not as immediate or shocking as oxygen at under 300 million years, but it is in some ways more haunting. Molecules like these do not only require stars, they require the lingering aftermath of stellar evolution. They require a universe that has already spent time cooking, shedding, mixing, and reassembling material into increasingly elaborate forms. Their early appearance suggests not only that the first galaxies are bright and active, but that some corners of the young cosmos are already running full chemical factories. Laid side by side, these detections create a pattern more troubling than any one of them alone. Oxygen appears very early. Nitrogen follows with an abundance pattern that strains the clock. Complex carbon-rich molecules emerge while the universe is still in what textbooks treat as an opening era. The details differ from object to object, and every one of them carries uncertainties. Spectra are difficult. Signal can be weak. Interpretation depends on models of stellar populations, gas conditions, and dust. Yet the repeated direction of the evidence matters. The early universe keeps looking pre-enriched, as if chemistry begins with an advance no one remembers giving it. That phrasing is not a claim that matter existed in its modern state from the start. It is something quieter and stranger. The expected pace of enrichment keeps appearing too slow. The observations suggest either that the first stars and galaxies process matter with an efficiency unlike anything seen later, or that some channels of early chemical evolution are missing from the usual catalogue, or that the timeline connecting redshift to available history is being misunderstood in a deeper way. This is where the emotional force of the problem shifts again. The earliest galaxies no longer resemble mere oversized seedlings. They begin to resemble ecosystems already partway through their internal cycles. Dust, metals, radiation, star formation, and possibly black hole activity all seem to be interacting much sooner than the standard picture anticipates. It is not just that there are galaxies too early. It is that these galaxies sometimes seem to have memories. Their spectra carry the marks of earlier events, earlier stars, earlier deaths. They are full of after effects. That is a difficult quality to assign to a universe still supposed to be near the beginning of visible structure. Once this impression settles in, the imagination naturally widens. If oxygen and nitrogen and molecular complexity appear so quickly, then perhaps the first generation of stars is unlike anything that survives into the modern universe. Perhaps the earlier stellar nurseries are denser, hotter, more collision-rich, more unstable. Perhaps giant stars live and die in numbers never seen again. Perhaps the first galaxies are not built in one slow chain, but in bursts layered on bursts, each one amplifying the next. Or perhaps the objects under discussion are not purely ordinary galaxies at all. A source that looks chemically advanced may be hiding extreme radiation fields, compact black holes, or unusual gas structures that mimic or accelerate mature spectral signatures. The possibility lingers because the catalogue of early universe objects is expanding under observation faster than theory is expanding ahead of it. One detail becomes impossible to ignore. Chemical maturity is difficult to fake. A galaxy may be misweighed, it may be reclassified. But when light reveals processed elements, it reveals elapsed work. The universe has already done something before the photons leave. That is why the chemistry crisis reaches deeper than headlines about impossible galaxies. It touches the order of events itself. If the early cosmos is already oxygen-rich in places, nitrogen-heavy in others, and carrying complex molecules before the end of its first billion years. Then the textbook sequence of simple to complex, slow and layered and orderly, is no longer a comfortable description. Something is compressing the chemical clock. Something is forcing cosmic history to fold inward on itself. And if stars are enriching their surroundings this quickly, then another possibility begins to loom behind the spectra. Perhaps some of the most powerful engines in the young universe are not stars alone. Perhaps there are deeper cores hidden inside these early systems, feeding, heating, and growing with a speed that ordinary galactic evolution should not allow. The chemistry begins to point toward that possibility, because a universe capable of maturing this fast may also be capable of building monsters at its center before the galaxies around them are fully born. A galaxy can appear too bright and still leave room for argument. A spectral line can arrive too early and still be pressed into an extreme but not impossible timetable. A black hole weighing tens of millions of suns only a few 100 million years after the Big Bang is harder to soften. The reason is not merely size, it is speed. Black holes do not grow without consequence. They feed, they radiate, they push on the matter falling toward them, and those processes set limits. When James Webb and other observatories begin uncovering evidence for enormous black holes in the young universe, the mystery changes once again. It is no longer only that galaxies look old before their time. It is that some of the darkest objects in nature seem to have outrun the physics that is supposed to build them. One of the clearest examples emerges from a galaxy known as UHZ1. It lies at a redshift of around 10, which places it roughly 470 million years after the Big Bang. Even that timing is enough to make any central black hole interesting. But the real disturbance comes from the way the object is found and what its light implies. The galaxy sits behind the massive cluster, Abell 2744, whose gravity warps space and acts as a natural magnifying lens. This effect, gravitational lensing, allows telescopes to see sources that would otherwise be too faint. James Webb identifies the lensed galaxy in infrared light. Then the Chandra X-ray Observatory, after staring at the same region for a very long exposure, detects X-rays coming from it. X-rays from such a distant system are a powerful clue. They strongly suggest gas is falling into a compact object and heating to extraordinary temperatures on the way in. In other words, there is likely an active galactic nucleus there, a feeding black hole. The inferred mass of that black hole is startling. It appears to be on the order of 40 million solar masses. By itself, that number is large. But what truly unsettles astronomers is the ratio between the black hole and the galaxy around it. In the nearby universe, central supermassive black holes are real and important, but they're usually only a tiny fraction of the stellar mass of their host galaxies. The black hole at the center of the Milky Way weighs a few million suns inside a galaxy containing hundreds of billions of stars. It is not negligible, but it is not the galaxy. In UHZ1, by contrast, the black hole may contain a substantial fraction of the total stellar mass of the host, perhaps comparable to it. That is not merely unusual, it suggests a different order of construction. In the standard picture, stars and galaxies come first, black holes start small, and then over time the black holes grow inside these already assembled systems. UHZ1 hints at the reverse. The foundation may be black, compact, and already massive while the galaxy is still catching up. That inversion matters because it cuts against one of the quiet assumptions built into ordinary cosmic history. Black holes are usually treated as products of galaxies. The deepest early observations begin suggesting that at least some galaxies might instead be products of black holes. The growth problem makes this more than a poetic inversion. Under the conventional path, a black hole begins as the remnant of a massive star, perhaps around 100 solar masses or less, and then grows through accretion and mergers. But accretion has a built-in limit known as the Eddington limit if gas falls in too fast. The radiation produced by that infall pushes outward strongly enough to slow the process. This does not make rapid growth impossible, but it does make it mathematically difficult. A small black hole growing steadily at the Eddington rate still needs a great deal of time to reach tens of millions of solar masses. UHZ-1 seems to offer less time than the standard route comfortably requires. The black hole is already too large, too early, and perhaps too dominant. This is why the idea of heavy seeds becomes more than a speculative side note. Instead of beginning with a small stellar remnant, perhaps some early black holes begin large. In the direct collapse scenario, vast clouds of primordial gas do not fragment into ordinary stars at all. Because the gas lacks metals, cooling can be inefficient, and under the right conditions the cloud may avoid breaking into small pieces. If it remains coherent and massive enough, the whole structure can collapse inward and form a black hole directly, perhaps with 10,000 or even 100,000 solar masses from the start. Such an object is not a grown black hole, it is born heavy. From there, continued accretion can build it into the range observed in systems like UHZ-1 within the available time. The arithmetic suddenly becomes less absurd. Yet the direct collapse solution does not arrive free of tension. It requires a narrow environment. The gas must remain nearly pristine. It must avoid fragmentation. It must lose angular momentum efficiently enough to fall inward. It may require a nearby source of radiation to suppress ordinary star formation while still allowing collapse. These are not impossible conditions, but they are special. The irony is sharp. James Webb is already telling astronomers that heavy elements seem to appear earlier than expected. Chemically enriched gas narrows the window during which pristine conditions can survive. So the same telescope that pushes heavy seed black holes toward plausibility also seems to threaten the pristine stage the model prefers. Again, the anomaly is not isolated. Every solution touches another problem. This is why the black hole story becomes so compelling. It is not simply another early surprise. It behaves like a central thread tying several others together. If black holes can form large and early, they can help explain excessive luminosity, rapid heating, unusual emission features, and the presence of active nuclei in tiny systems. If they come first, then some of the early galaxies seen by James Webb may not be ordinary stellar assemblies in the modern sense. They may be structures forming around already dominant gravitational engines. The host galaxy becomes secondary, a settling shell around a dark core that was there almost from the start. This possibility begins to reframe the young universe. It no longer looks like a place where small stellar systems gradually discover complexity. It starts to look like a place where some of the deepest structures are established first and everything luminous must adapt around them. Black holes in this view are not late-stage fossils of stellar death. They are prime movers in early architecture. There is an eerie logic to this. Black holes are excellent at organizing matter without producing stable visible structure of their own. They pull, they heat, they transform gas into radiation and pressure. If the first billion years contains black holes that are already overgrown relative to their hosts, then perhaps the apparent maturity of some early galaxies is partly an illusion of perspective. Perhaps what is being seen is not a galaxy that has had time to age naturally, but a region forced into rapid development by a black hole whose growth began earlier than expected and reshaped its surroundings. UHZ-1 is not the only reason this thought gains traction, but it is one of the clearest. It is a lensed glimpse of a universe in which central engines may outrun their environments. There is also a psychological change in the evidence here. Big galaxies too early are one kind of threat to the standard model. Overmassive black holes are a deeper one because black hole growth depends on hard physical limits, rather than only on the uncertain conversion of light to stellar mass. There are still uncertainties, of course. Masses of distant active black holes are not measured with perfect ease. Lensing models matter. X-ray counts are faint. host galaxy properties can be difficult to disentangle. Yet even with those caveats, the broad conclusion remains disturbing. Very early black holes appear to exist in a regime where ordinary light-sea growth strains credibility. Once that is admitted, speculation begins to widen, but carefully. Maybe heavy seeds are common. Maybe direct collapse is not a rare corner case, but a standard early universe channel. Maybe primordial gas clouds under early conditions behave in a more coherent and catastrophic way than later gas ever does. Maybe a first generation of colossal stars collapses almost immediately into oversized remnants. Or maybe some unseen source of support or heating changes the whole route by which matter sinks toward dark centers. Whatever the correct answer, a simple progression from stars to remnants to slow black hole growth begins to look incomplete. And then an even stranger thought enters. If black holes can form before their galaxies fully exist, perhaps there is a visible phase in which the black hole is not yet naked and the galaxy is not yet real. Perhaps there is an intermediate object, compact, bright, red, and unlike anything in the nearby universe, where the core is already present but the surrounding system is still a temporary cocoon. That idea will matter later. For now, the important shift is this. The early universe is no longer only overproducing stars and chemistry. It may also be producing central darkness at impossible speed. The galaxies are not merely bright too soon. Some may be orbiting a deeper reversal in cosmic order, one in which gravity gathers itself into black holes first and lets the rest of structure follow behind. The black hole problem becomes harder to ignore once it stops appearing as a rare freak case and starts showing up as a population. That is what happens when astronomers working through James Webb survey fields begin noticing a peculiar class of faint, compact sources that do not fit comfortably into any familiar category. At first they look modest enough, little more than reddish points scattered through the deep images. They are small, in some cases barely resolved even by Webb. They are red, which in early universe work often means one of two simple things. Either the objects are very distant and their light has been stretched by cosmic expansion, or they contain dust that absorbs bluer light and leaves the longer wavelengths more visible. For a while, that is how they're treated. They are catalogued as compact high redshift galaxies, interesting but not yet revolutionary. There is no immediate reason to think otherwise. Deep fields are full of strange-looking sources, and most of them eventually settle into ordinary explanations. But this class does not settle. It grows stranger with every layer of attention. The informal name Little Red Dots begins almost as a convenience. It is descriptive rather than theoretical, a label for what the objects look like before anyone knows what they are. That uncertainty matters. A name built from appearance is a sign that classification has failed to catch up with observation. The little red dots are compact, numerous, and oddly concentrated in the first few billion years of cosmic history. They keep appearing across multiple surveys. They are not isolated curiosities from one field or one pipeline. The more James Webb observes, the more this population seems to be a real component of the young universe. And when spectra begin to arrive, the idea that they are simply small galaxies starts to fray. A spectrum is where an object begins telling on itself. Broadband imaging can suggest brightness, colour, and shape, but spectroscopy reveals internal conditions. It shows what kinds of atoms are present, how gas is moving, how intense the radiation field is, whether a source is dominated by stars or by something more compact and violent. For the little red dots, these spectroscopic fingerprints are deeply uncomfortable. Many show signs consistent with active galactic nuclei, which means they appear to harbour feeding black holes. That alone would be striking, because the implied number density of active black holes at those epochs seems far higher than standard models predict. but the real tension comes from the combination of activity and scale. The hosts are too small. In the nearby universe, galaxies with active central black holes are usually much larger systems. Their structures are extended. Their stars occupy tens of thousands of light years. The little red dots, by contrast, are packed into volumes less than 1,000 light years across, sometimes much less. They look less like ordinary galaxies with active nuclei and more like some compressed, transitional state that does not survive into later cosmic times. The population also seems bounded in time. It clusters strongly between redshifts of roughly 5 and 10, which corresponds to a period beginning within the first billion years and extending into the next. Then it fades from the record. Below a certain redshift, the class no longer appears. Not gradually, not as an evolving tail that can be traced into a modern counterpart, but almost as though an entire kind of object has completed its phase and disappeared. This is one of the most unnerving features of the little red dots. Astronomers are accustomed to galaxy evolution. Spirals merge into ellipticals. Irregular systems settle into disks. Star-forming populations redden and fade. The universe changes its appearance with time, but usually in ways that preserve ancestry. There are predecessors and descendants. The little red dots resist that family tree. They appear, persist for a limited cosmic window, and then leave no obvious heirs. It begins to feel less like a new subtype of galaxy, and more like a brief stage in some other process. The most famous and puzzling example among them becomes known as the cliff. The name comes from a spectral feature that drops so abruptly it resembles a sudden edge, rather than the gentler patterns familiar from ordinary galaxy templates. The feature resembles a Balmer break, a well-known signature associated with hydrogen absorption and often used to infer the age and composition of stellar populations. But in this case, the shape does not sit comfortably within known models. It is too steep, too odd, too unwilling to behave like a standard combination of stars, dust, and black hole emission. The spectrum seems to belong to something real and luminous, yet not to anything already present in the theoretical catalogue. This is the moment when the mystery of the little red dot ceases to be mainly statistical and becomes conceptual. The problem is not only that there are too many of them, or that they vanish later. The problem is that at least some of them seem to be built from ingredients nobody knows how to arrange. Once that happens, the field does what it always does when observation outpaces classification. It begins proposing intermediates, hybrids, transitional forms. Maybe the little red dots are unusually dusty compact galaxies. Maybe they are active nuclei wrapped inside very dense stellar systems. Maybe they are young galaxies caught during a short-lived burst phase. Maybe they are the remnants of mergers. Maybe their black holes outshine their stars and distort the interpretation of everything around them. Each idea captures a piece, but none closes the case. The spectra remain too strange, the compactness too extreme, the abundance too high, and the disappearance too clean. One proposal begins attracting particular interest precisely because it explains several otherwise disconnected properties at once. In this picture, the little red dots are not really galaxies in the mature sense at all. They are black hole cocoons. The black hole is already there, perhaps formed through direct collapse in the early universe, already large compared with anything a stellar remnant route should comfortably allow. Around it sits a dense envelope of gas, heated from within by the black hole's accretion. The gas glows. The cocoon radiates across infrared wavelengths. From a great distance it can mimic the appearance of a compact galaxy because it is luminous, red, and extended enough to be seen, but only barely. Crucially, it is temporary. As the black hole feeds, the envelope is either consumed or blown away. What remains is the dark central object, perhaps later embedded within a more ordinary galaxy that forms around it over much longer timescales. This hypothesis changes the emotional geometry of the early universe. It suggests that some of the sources James Webb first takes for galaxies are really incubation phases. They are not cities of stars already in place. They are glowing shells around gravitational cores, the visible skin of something darker and more fundamental. That would explain why the objects are so compact. It would explain why they can host active nuclei so early. It would explain why they disappear. The cocoon is a phase, not a final state. It would also connect naturally to systems like UHZ1, where the black hole seems overgrown relative to the galaxy. In this framework, there is no anomaly in the ratio. The black hole is not disproportionately large because the galaxy failed to grow. It is disproportionately large because the black hole came first. The galaxy is the latecomer. What makes this idea more than a poetic image is how many separate oddities it begins to line up. The abundance of little red dots would imply that early black holes are common, perhaps vastly more common than expected. Their compactness would cease to be embarrassing. Their spectra, including the cliff, would no longer need to fit ordinary stellar templates because they would not be dominated by ordinary stellar populations. Their disappearance below lower redshift would no longer be mysterious because the phase itself would have ended, leaving behind objects that James Webb no longer identifies in the same way. It is a tidy explanation, perhaps too tidy, which is why it remains a hypothesis rather than a conclusion. Spectroscopy is still being analysed. Alternative models are still being tested. The objects themselves are faint, distant, and difficult. Yet the very fact that such a model now feels necessary says something profound. The early universe has produced a population that the standard taxonomy of galaxies, quasars, and active nuclei does not comfortably absorb. That is not a small failure of naming. It means the inventory of cosmic objects may be incomplete, especially at the beginning. This matters because cosmology depends on counting the right things. If the early universe is being surveyed under the assumption that every bright compact source must be some kind of galaxy, then the inferred history of galaxy formation, stellar mass buildup, and rionization can all be distorted. The little red dots raise the possibility that astronomers are not only surprised by how early structures appear, they may also be misidentifying the structures themselves. A source counted as a galaxy might instead be a black hole in a brief luminous stage. A brightness interpreted as starlight might instead be the glow of heated gas surrounding a central engine. A compact red smudge in a deep field might be less like a young galaxy and more like a chrysalis. Once that possibility is admitted, the boundary between observation and speculation becomes unusually fertile. If black hole cocoons are real, then the centres of many later galaxies may trace their ancestry not to ordinary stellar collapse but to these early, bright, vanishing seeds. If they are not real, then something equally unfamiliar still has to explain the spectra, the abundance, and the disappearance. Either way, the little red dots do not return the universe to safety. They deepen the sense that the first billion years contain stages of visible, cosmic evolution no textbook had room for. And somewhere behind that idea lies an even stranger possibility. If some early compact sources are not galaxies but temporary envelopes around black holes, then perhaps some others are not galaxies because they are not many objects at all. Perhaps they are single colossal bodies whose light only imitates a galaxy from far away. That thought remains speculative, but James Webb begins to make it harder to dismiss, especially when one faint spectral whisper appears at a wavelength that should not matter so much, and yet threatens to change the meaning of several of the brightest points in the early sky. The next possibility sounds at first like a mistake in naming, but it may be something stranger than that. A distant bright source is often called a galaxy because, at great enough distance, a galaxy and a compact luminous object can begin to look alike. Both can appear as tiny red points in the deep infrared images of the James Webb Space Telescope. Both can sit at extraordinary redshift. Both can hide their internal structure behind the limits of resolution and faintness. In most eras of astronomy, this ambiguity does not matter very much, because the available categories are stable. A bright source at cosmological distance is usually some combination of stars, gas, dust, and perhaps a feeding black hole. But the early universe seems to be eroding that comfort. Once little red dots begin resisting every ordinary label, and once some black holes appear too massive to have grown by familiar roots, another idea moves from the outer edge of theory toward the centre of the conversation. Perhaps some of the most distant objects are not galaxies at all. Perhaps they are single colossal bodies, powered not by normal stellar fusion alone, but by the annihilation of dark matter trapped inside them. The proposal is old enough to have begun as pure theory, long before the James Webb Space Telescope launches. In that theoretical picture, dense halos of dark matter gather around primordial gas clouds in the earliest universe. If dark matter consists of particles capable of annihilating when they encounter one another, then under the right conditions those collisions release energy into the surrounding gas. Instead of collapsing straight into an ordinary first-generation star, the cloud can remain puffed up, heated from the inside by a source no ordinary star uses. The result is called a dark star, though the name misleads by sounding dim. A dark star in this idea is not dark in appearance. It can be among the brightest objects in the early cosmos. The darkness belongs only to the fuel. This matters because dark matter has always occupied a peculiar role in cosmology. Its gravitational influence is everywhere and undeniable. Galaxies rotate too fast to be held together by visible matter alone. Clusters of galaxies lens light more strongly than their luminous content permits. The large-scale structure of the universe forms as though most of its matter is invisible. Yet dark matter itself has never been caught directly in a detector or a collider. It is inferred, mapped through gravity, and built into the standard model of cosmology, but it remains physically elusive. A dark star would change that emotional balance. It would not be direct detection in a laboratory sense, but it would mean dark matter is doing something visible, something energetic, something capable of producing light through its interaction with ordinary gas. That would be extraordinary, even if it concerned only one object. In the context of the James Webb discoveries, it becomes more than extraordinary. It becomes dangerously useful. A supermassive dark star could imitate a young galaxy in exactly the way the current crisis seems to need. It could shine with the luminosity of many millions or billions of ordinary stars while remaining physically compact. It could sit at extreme redshift as a bright unresolved source. It could confuse the census of the early universe by inflating the number of objects interpreted as galaxies. It could also help with the photon budget of reionization, because such an object would produce intense ultraviolet radiation capable of ionizing the surrounding hydrogen. A single new category would begin solving multiple problems at once. That is often where caution becomes necessary. In science, a model that appears to fix many puzzles can be attractive for the wrong reasons. Elegance is not the same as proof. Yet the reason dark stars remain alive as a possibility is not elegance alone. It is the uncomfortable fact that the early universe keeps producing sources whose brightness and compactness can be read more than one way. By the middle of the decade, a handful of particularly distant candidates are discussed as possible dark stars rather than galaxies. At first, these are only photometric candidates, which means their colours and brightness fit the expectations of the model without proving the identity of the source. Photometry is suggestive but never decisive here. It says the object could be a dark star, just as it could be a small galaxy with unusual stellar populations. The only serious path forward is spectroscopy. The light must be split into wavelengths fine enough to reveal whether the physical conditions correspond to ordinary stars, an active nucleus, or something more exotic. This is where one of the most distant known objects becomes central again. The galaxy, already famous for its extraordinary distance and early oxygen signature, also becomes the site of a much fainter and more speculative clue. In the spectral data of that remote source, astronomers identify a tentative absorption feature near 1,640 angstroms, associated with doubly ionized helium. This line matters because helium is hard to ionize twice. It takes an unusually harsh radiation field, one capable of producing extreme ultraviolet photons. In the modern universe, such conditions are linked to very energetic environments, powerful active nuclei, certain rare stellar populations, and other violent sources. In an object seen only a few 100 million years after the Big Bang, the appearance of such a feature is deeply provocative. The signal is weak. Its statistical significance is low enough that no one careful should call it a detection. It may be real. It may be an artifact of noise, reduction choices, or line confusion. But if it is real, it sits exactly where the dark star model predicts one of its most distinctive signatures. This is the moment where the script of the early universe threatens to split in two. Under the ordinary reading, the remote source is a galaxy that is already chemically mature, already bright, and already difficult to explain. Under the more speculative reading, it may not be a galaxy at all, or at least not purely one. It may be dominated by a single supermassive dark star, perhaps surrounded by additional structure, perhaps already on its way toward collapse. The difference between these readings is enormous. If the object is a galaxy, then the crisis remains mainly about accelerated formation and early enrichment. If it is a dark star, then the crisis reaches into the nature of dark matter itself and the basic inventory of what existed during cosmic dawn. Either way, the stakes are high, because both readings imply the early universe is stranger than expected. The dark star route simply pushes the strangeness deeper. It also connects naturally to the little red dots and the heavy seed black hole story. In one speculative chain, primordial gas inside dark matter halos forms a dark star rather than an ordinary first star. That object grows to enormous mass while its dark matter fuel holds it in an inflated, luminous state. When the dark matter support weakens or the object destabilizes, it collapses into a massive black hole seed. Gas then continues to fall inward, surrounding the seed with a glowing cocoon. For a brief period, the object resembles one of the compact red sources James Webb finds in abundance. Later the cocoon clears, the black hole remains, and a more familiar galaxy gradually forms around it. This sequence is not confirmed. It is a stitched-together possibility drawn from multiple anomalies, and every stitch remains under tension. But what makes it powerful is that it offers continuity. The impossible galaxy brightness, the missing ionizing photons, the overmassive early black holes, and the little red dots all begin to look less like separate failures and more like chapters in the same unseen life cycle. The universe may not be violating one rule in 10 different ways. It may be revealing an early mode of structure formation that current categories carve up incorrectly. Even if dark stars themselves turn out not to exist, the fact that the idea survives serious attention says something important about the state of cosmology. The observed objects are strange enough to make an energy source based on undetected matter seem less extravagant than forcing them into old boxes. That is a remarkable reversal. For decades, dark matter has been treated as a gravitational necessity and a laboratory frustration, present everywhere in theory and nowhere in direct experience. Now, one of the most advanced telescopes ever built is producing data that tempt astronomers to ask whether dark matter, may once have lit the sky. There is another reason the dark star idea lingers. The early universe appears to reionize faster than the known supply of ordinary galaxies and quasars comfortably allows. Reionization is the phase when ultraviolet light from the first luminous sources strips electrons from the neutral hydrogen, filling intergalactic space, gradually making the universe transparent. The standard picture assigns this work to young galaxies, and perhaps a modest contribution from early active nuclei. But if the process finishes earlier than expected, then the photon budget becomes tight. There seem to be too few known sources producing too few ionizing photons too soon. Dark stars, if common enough, could help close that gap. They would pour harsh radiation into the surrounding medium and then vanish from later epochs, when their special fuel source was exhausted. Again, the pattern is tantalizing. An object that would naturally be invisible today could explain both early light and present absence. It is difficult not to notice how often the James Webb results invite solutions based on transient categories, things that exist only briefly and leave little clean trace afterward. The early universe begins to look populated not just by young versions of modern objects, but by temporary classes that disappear once the cosmos exits its initial conditions. That possibility carries a quiet consequence. If transient objects dominate the first few 100 million years, then modern astronomy has been trying to reconstruct the beginning from descendants that may preserve only part of the story. The nearest universe may be a poor teacher for the farthest one. Familiar stars, familiar galaxies, familiar active nuclei may not capture what matter does under the raw pressures of cosmic dawn. In that sense, the dark star idea is valuable even before it is proved or disproved. It forces the imagination of astrophysics to widen only where the data has already made old expectations too narrow. The whisper near 1,640 angstroms remains only a whisper. It does not yet carry the authority needed to change textbooks. But the fact that such a faint feature can suddenly matter so much reveals how unstable the interpretation of the early universe has become. A single confirmed line could reclassify the most distant known object. A single non-detection in deeper data could send theory back to the drawing board. The frontier is now sensitive to very small spectral details, because those details decide whether the sources in question are galaxies, cocoons, stars, or something that crosses the boundaries between all three. This is the strange calm at the centre of the James Webb era. Nothing has yet been conclusively overturned, and yet the path of least surprise keeps disappearing. If the brightest remote points are galaxies, they form too quickly and enrich too soon. If some are dark stars, then dark matter has left an observable mark on luminous history. If some are cocooned black holes, then galaxies may not be the first visible architecture after all. Every route leads away from simplicity, and while observers continue testing these possibilities in the deep past, another pressure is building in a different part of cosmology, one that seems at first unrelated. It concerns not the objects inside the universe, but the universe itself and the rate at which its space expands. For years, that rate has refused to agree with itself. Now, as the James Webb results accumulate, the disagreement begins to look less like an awkward measurement problem and more like a sign that the bridge between the early cosmos and the later one may be bent. The mystery becomes more dangerous when it leaves the galaxies and begins touching the framework used to date them. Until this point, the pressure has mostly fallen on the contents of the universe. Galaxies appear too mature. Black holes appear too heavy. Chemistry appears too advanced. The natural instinct is to keep the background intact and search for some local fix inside early astrophysics. Perhaps stars form differently at high redshift. Perhaps black holes receive heavier seeds. Perhaps the census of distant sources is incomplete. But there is another possibility, quieter at first and then difficult to ignore. Perhaps the problem is not only with the objects appearing in the young universe. Perhaps the trouble also lies in the way cosmology translates redshift into time, distance, and history. That possibility enters through a different long-running crisis, one that predates James Webb and concerns a single number, the present rate of cosmic expansion, known as the Hubble constant. In principle, this number should be among the cleanest in astronomy. The farther away a galaxy is, the faster it recedes as space itself expands. Measure distances, measure recession speeds, relate the two. The result should say how quickly the universe is stretching today. In practice, the task is difficult because measuring cosmic distance is one of the oldest and most delicate arts in observational astronomy. Light grows faint with distance, but faintness alone is not enough, because intrinsic brightness varies from object to object. Astronomers therefore build a ladder. They calibrate one kind of standard candle nearby, then use that to calibrate another kind farther out, and so on, until the distances reach well into the expanding universe. Over decades, the ladder becomes more precise and more carefully checked. The modern local determination relies heavily on Cepheid variable stars, whose pulsation periods reveal their true luminosities, and on Type 1 a supernovae, whose explosions serve as luminous markers across enormous distances. This route gives a value for the expansion rate around the low 70s in kilometers per second per megaparsec. Meanwhile, there is another route that does not begin in the local universe at all. It begins with the cosmic microwave background, the afterglow of the Big Bang released when the universe is only about 380,000 years old. Satellites such as Planck map tiny fluctuations in that ancient radiation with extraordinary precision. Those fluctuations encode information about the early cosmos. If the standard cosmological model is assumed, then the pattern in the microwave background predicts what the expansion rate should be today. That route gives a lower value, around the high 60s. The two answers do not agree. The gap is not trivial. It is persistent, statistically strong, and deeply irritating because both methods are internally careful. For years, the safest assumption is that one side must be missing a systematic error. Perhaps local distance measurements are biased by dust, crowding, blending, or subtle calibration issues. Perhaps the early universe inference carries some hidden assumption that only looks firm because the model around it is accepted so widely. But as the measurements improve, the disagreement survives. This is the Hubble tension, and its significance grows because science does what it is supposed to do and still fails to make the numbers converge. This is where James Webb enters a problem it did not create. One of the major criticisms of the local distance ladder has always concerned resolution. In crowded distant galaxies, Cepheid variables can blend with nearby stars in lower resolution images, making them appear brighter than they are, and therefore making the inferred distances too small. A smaller distance would then push the derived expansion rate too high. This criticism is reasonable, and for years it hangs over the local measurements as a plausible escape hatch. James Webb weakens that hatch. Its sharper infrared view can separate stars that the Hubble Space Telescope often sees as blended light. When teams reobserve crucial Cepheid fields with James Webb, the discrepancies are real, but too small. The local measurements do not collapse downward to meet the value inferred from the cosmic microwave background. The gap remains. This is a subtle but profound moment. James Webb is not only finding galaxies that seem too advanced in the early universe, it is also helping confirm that the cosmic timeline connecting the early and late universe may itself contain a fault. There is a third route, built to avoid some of the arguments between these two camps. It uses the tip of the red giant branch, a phase in stellar evolution, where old red giant stars reach a fairly uniform peak brightness before helium ignites in their cores. This method is less sensitive to some of the crowding and dust issues that affect Cepheids. yet its results tend to fall between the two main camps rather than resolving the conflict. That does not calm the situation, it complicates it. Instead of one side being plainly wrong, the field begins to look like it contains multiple partially reliable measurements that will not fit into a single tidy model. At this stage, the question changes. Perhaps the problem is not an error in any one measurement. Perhaps different methods are sampling different aspects of a universe whose expansion history is not being described completely by the standard model. Once that possibility becomes legitimate, the James Webb anomalies start to feel less isolated. If the map from redshift to cosmic age is even slightly off, because the expansion history is wrong in detail, then every early universe calculation inherits that distortion. Distances shift, luminosities shift, the amount of time available for galaxy growth shifts, black hole growth limits shift, star formation timescales shift, chemical enrichment windows shift. No single correction would magically erase all the anomalies, but a change in the background model could loosen many of them at once. That is why the Hubble tension matters so much here. It is not only a dispute about one number, it is a sign that the bridge between the primordial universe and the modern one may have been built with a missing piece. Then another instrument begins applying pressure from a different angle. The dark energy spectroscopic instrument, mounted on a telescope in Arizona, is designed to map the large-scale structure of the universe across billions of years by taking spectra of millions of galaxies and quasars. Its power lies in numbers and geometry. Buried in the distribution of galaxies is a relic pattern from the early universe, a preferred scale left behind by sound waves in the hot primordial plasma. This scale acts like a standard ruler. By measuring how it appears at different redshifts, astronomers can reconstruct how cosmic expansion evolves over time. The key term here is dark energy, the mysterious driver of the universe's accelerated expansion. In the standard model, dark energy is treated as a cosmological constant. It has the same strength everywhere and at all times. Its equation of state parameter is fixed at a value of -1. This assumption has been central to cosmology for a quarter of a century. It is elegant because it is simple. It keeps the large-scale model stable. It also turns the late universe into something conceptually quiet. Space accelerates outward under a steady invisible pressure, and the future becomes a slow thinning into darkness. But the new survey data begins to suggest that dark energy may not be constant after all. The early hints are not definitive. In physics, a suggestive signal is often where humility begins, yet the direction matters. Instead of clustering tightly around the value expected for a constant cosmological term, the measurements begin leaning toward a weaker, evolving form of dark energy, something that changes over cosmic time rather than remaining fixed. The statistical significance grows as more data is processed. It does not yet command universal surrender, but it rises high enough that cosmologists can no longer treat it as noise without argument. This is where the stage itself begins to move. If dark energy evolves, then the standard timeline connecting early and late cosmic history changes. A galaxy seen at extreme redshift would still be distant, still ancient, still extraordinary, but the exact age of the universe at that redshift could shift slightly. The densities, temperatures, and growth intervals available to early structures could shift with it. On paper, these changes may sound modest. In practice, they can ripple through every interpretation made from James Webb data. Cosmologists begin exploring modified models in which dark energy is stronger or behaves differently at earlier times and then weakens later. Under some of these alternatives, several separate tensions ease simultaneously. The Hubble constant inferred from the early universe drifts closer to the locally measured value. The time available for early galaxy formation changes slightly. The most impossible black holes become less impossible. The brightest early sources remain strange, but the strain on the models lessens. This is not a final resolution. It is more like the discovery of a hinge. A single alteration in cosmic expansion history can partially relax several problems that had previously seemed unrelated. That is scientifically seductive for good reason. When one modification helps with multiple independent tensions, it looks less like a patch and more like a clue. Yet there is danger here too. More flexible models often fit data better simply because they possess more freedom. Extra parameters can mimic understanding while only absorbing discrepancy. The crucial question is whether the modified dark energy behavior corresponds to real physics or merely to mathematical generosity. That remains unsettled. Still, the philosophical temperature of the crisis changes. The James Webb anomalies no longer look confined to an obscure corner of early galaxy astrophysics. They begin connecting to the most fundamental model of expansion itself. This changes the mood of the evidence in a very specific way. Before, it is possible to imagine that James Webb is revealing extraordinary edge cases within an otherwise stable cosmic background. Now the background may also be in play. The sense of early maturity in distant galaxies, the rapid appearance of chemistry, the overgrown black holes, and the unresolved expansion tension all begin to point toward the same uncomfortable idea. The standard history of the universe may be slightly mistimed from the inside out. Not catastrophically wrong, not overturned in one blow, but off enough in its connecting logic that the first billion years no longer land where the textbooks place them. If that is true, then the consequences extend beyond explanation and into destiny. A constant dark energy leads to endless acceleration, a universe that thins forever. A weakening dark energy opens other futures. Expansion could continue but slow. The long-term fate could become less simple, perhaps even allowing gravity to matter again on the larger scales. No one can responsibly draw a clean line from present hints to a final cosmic ending. The timescales are too vast and the uncertainties too easily amplified. But the fact that such futures return to serious discussion is itself revealing. The James Webb era does not merely make the beginning look strange, it destabilizes the assumptions that once made the future seem predictable. For the purposes of the early universe, what matters most is the broken bridge between then and now. If the bridge is bent, every age estimate derived by crossing it becomes suspect in detail, not meaningless, but vulnerable. A redshift is still a measured fact. The cosmic interpretation attached to that redshift becomes newly negotiable. That is enough to change the tone of every anomaly. A galaxy that is too massive under one expansion history may be less extreme under another. A black hole that seems mathematically impossible may become merely improbable. A chemical signature that appears outrageously premature may still be early, yet not quite as impossible as it first seemed. Notice what this does not do. It does not restore comfort. It simply spreads the mystery across a larger canvas. The first galaxies remain startling. The little red dots remain unidentified. Dark star hints remain unresolved. The Hubble tension remains real. The new expansion data does not solve the puzzle, so much as reveal that the puzzle may be systemic. The early universe might not be violating a settled cosmic clock. The clock itself may be under revision, and once that thought settles in, the next question comes almost automatically. If the first galaxies, the first black holes, the first chemical factories, and the expansion history of space all point in the same direction, then perhaps the problem is not that one class of object formed too early. Perhaps entire levels of cosmic structure did. The disturbance stops looking local once it rises above the scale of individual galaxies. For a while it is still possible to imagine that the early universe is merely producing a few exceptional objects, a handful of galaxies that form too quickly, a few black holes that begin from unusually heavy seeds, a few spectra whose chemistry matures at impractical speed. Exceptional objects can always be granted exceptional stories. Cosmology is large enough to contain outliers. But when entire environments begin appearing ahead of schedule, when dusty giant systems, crowded associations of galaxies, and the clearing of intergalactic fog all begin happening earlier than the standard picture expects, the anomaly changes character. It no longer concerns rare monsters hidden in deep fields. It starts to resemble a general acceleration of cosmic history itself. One of the clearest expressions of this comes from the discovery of massive dusty galaxies in the first billion years, objects sometimes described as red monsters because of both their colour and their implied completeness. These systems are not merely bright or large in stellar mass. They look developed in several ways at once. Their light suggests substantial stellar populations. Their red appearance indicates either heavy dust, older stars, or both. Their inferred star formation histories imply that they have already been through substantial processing of gas into stars and of stars into heavier elements. This is a difficult thing for the standard story to absorb because dust is not a primitive ingredient. Dust is made from metals, and metals must first be forged inside stars. Then those stars must die, expel that material, and allow it to cool and survive in the surrounding medium. A dusty galaxy at early times is not simply a place with many stars. It is a place where enough generations of stellar activity have already occurred to seed the galaxy with the leftovers of stellar life. In other words, dust is not just matter, it is evidence of prior time. That is what makes the red monsters so unsettling. A galaxy can become bright very quickly under generous assumptions. A galaxy can perhaps even become massive more quickly than the standard simulations once believed, especially if the first stellar populations are top-heavy and luminous. But a galaxy that is already dusty, chemically processed, and structurally substantial within the first billion years looks less like a fast-growing child and more like a middle-aged system somehow transplanted backward into the dawn of the cosmos. The usual patches begin to collide here. A top-heavy stellar population may reduce inferred stellar masses because fewer massive stars can generate the same amount of light. But those same massive stars explode violently and can destroy dust grains as efficiently as they create the raw heavy elements that later dust requires. A violent burst of star formation can make a system bright quickly, but brightness alone does not guarantee the layered chemical cycling needed for dust to accumulate and persist. The fixes that help with one problem often sharpen the next. This is what gives the early universe its increasingly uncanny feeling. Every time one anomaly appears ready to be tamed, it reveals a shadow cast across another. The red monsters force attention onto completeness. They are not just too luminous or too massive. They look too finished. They seem to be running mature galactic ecosystems before the universe is supposed to have had time to lay down the ecological foundations. The puzzle rises another step when one moves from single galaxies to collections of them. A galaxy is one thing. A protocluster is something larger and slower by nature. Clusters are the great cities of the cosmic web, enormous gravitationally bound structures containing many galaxies and, in mature cases, hot gas spread between them. Their formation is not instantaneous because it depends on multiple prior layers of history. Galaxies must form first. They must then begin falling together along dark matter filaments. Their halos must interact. Gas between them must be shock-heated and stirred into an intracluster medium. The entire process unfolds over long timescales. That is why the identification of a protocluster containing dozens of galaxies only about 1 billion years after the Big Bang lands with such force. It is not merely that many galaxies are already in the same region. It is that the region seems to be behaving like a structure with shared dynamics, with hot gas present between members, as though assembly has already advanced beyond the first loose gathering. The hot gas matters because it is a sign of interaction, of energy already deposited on scales larger than single galaxies. It suggests a system beginning to act as more than the sum of its luminous parts. In the standard view, such organization should take longer. The gravitational choreography of cluster assembly is not impossible in a young universe, but it should still be at a comparatively embryonic stage. Finding a protocluster that already looks active and thermally processed 2 billion years earlier than expected does not just add another curiosity to the list, it expands the scope of the timing problem. Now the universe is not merely overproducing individual objects, it is assembling communities ahead of schedule. This is the point where the pattern becomes difficult to dismiss as coincidence. Massive galaxies too early could perhaps be measurement bias. Dusty galaxies too early could perhaps be unusual star formation histories. Overmassive black holes too early could perhaps arise from heavy seeds. But massive galaxies, dusty galaxies, early black holes, and proto-clustered environments all leaning in the same direction begin to suggest that the early universe is not simply throwing occasional surprises, it appears broadly overorganized. The same impression emerges in one of the most consequential transitions in cosmic history, rionization. After recombination, when protons and electrons first combine into neutral hydrogen and the cosmic microwave background is released, the universe enters a long period in which neutral hydrogen fills intergalactic space. Light does not yet travel freely across the cosmos the way it later will. Then the first luminous sources switch on and begin flooding their surroundings with energetic ultraviolet photons. These photons strip electrons back off hydrogen atoms, carving growing bubbles of ionized, transparent space through the fog. Eventually the bubbles overlap and the universe becomes largely transparent again. This is ruinization, one of the great turning points in the history of light. For a long time, the end of this process is placed around a redshift corresponding to roughly 1 billion years after the Big Bang. That timeline is not arbitrary. It is based on the known population of early galaxies and quasars, and the number of ionizing photons those sources should plausibly produce. James Webb complicates this in two different ways at once. On the one hand, it finds more luminous early sources than many expected, which might seem to help. On the other hand, it increasingly suggests that rionization may have ended earlier than the standard photon budget comfortably permits. If the fog clears sooner, then the universe must have received a more intense bath of ionizing radiation earlier than expected. This becomes the photon budget crisis. Add up the known galaxies, add plausible contributions from active galactic nuclei, and the total still seems short. There are not enough clear sources doing enough work quickly enough. Some component is missing. This is one of the reasons the other anomalies begin to feel connected rather than merely adjacent. Dark stars, if they exist, would help with the missing photons. Black hole cocoons might help as well. A hidden population of compact active sources could contribute. Even the little red dots, if many of them are early feeding black holes rather than ordinary galaxies, might alter the budget significantly. The crisis, therefore, does not point toward emptiness. It points toward incompleteness of inventory. The early universe seems to produce more radiation than the current catalogue of objects can supply. That sentence may be the quiet centre of the entire James Webb mystery. It does not merely say that some galaxies are surprising, it says that the census itself may be wrong. If the wrong things are being counted, then every higher-level conclusion inherits the error. The build-up of stellar mass, the timing of chemistry, the balance of ionizing photons, the meaning of compact red sources, even the inferred pace of reionization all become entangled. The universe may not be defying expectation one object at a time. It may be revealing that the expected cast of characters in Cosmic Dawn is incomplete. This possibility changes how the early structures are seen. A dusty giant no longer looks like a random early overachiever. It becomes evidence that the first billion years contained mature processes not fully included in the model. A protocluster no longer looks like a freak accident of rapid assembly. It becomes evidence that large-scale organization also emerged faster than anticipated. Reionization no longer looks like a technical timing dispute. It becomes a signal that the total radiative output of the early universe exceeds what the standard inventory can deliver. Once these pieces are placed side by side, the pattern acquires a quiet inevitability. Everything is too early. Everything is too complete. Everything seems to behave as though the first billion years is not an opening act but a compressed middle chapter. The standard model still holds enormous explanatory power elsewhere. It still describes the cosmic microwave background with exquisite success. It still reproduces large-scale structure at later epochs. It still serves as the backbone of modern cosmology. That is part of what makes the early anomaly so profound. The problem is not random failure. It is selective failure, concentrated where the universe first becomes visible and begins constructing complexity out of simplicity. The breakdown occurs at the threshold, at the transition from primordial smoothness to structured light. That location feels meaningful. It suggests that the missing physics, or the missing category of objects, or the missing piece of expansion history is tied specifically to the universe's first attempt at visible architecture. It may not require rewriting everything. It may require rewriting the beginning of the visible story. By now, the separate threads have started to braid together almost against intention. Overmassive galaxies imply accelerated growth. Blue compact systems imply extraordinary star formation efficiency. Early oxygen, nitrogen, and complex molecules imply accelerated chemistry. Overgrown black holes imply accelerated central collapse. Little red dots imply missing categories or transitional phases. Reionization implies missing radiation sources. Early protoclusters imply accelerated large-scale assembly. The Hubble tension and evolving dark energy hints suggest that even the backdrop connecting early and late history may not be fully correct. What had once looked like isolated disagreements begins to resemble a coherent misfit between the first billion years and the theory used to narrate them. The consequences of that misfit remain uncertain. Perhaps future observations will lower some masses again, reclassify some red dots, and soften the whole picture into something merely unusual. Perhaps a more flexible but still recognizably standard cosmology will absorb the evidence with a handful of carefully placed revisions. Or perhaps the early universe is revealing something deeper, that the starting conditions of visible structure carry hidden pathways not represented in any of the old simulations. Pathways in which black holes form first, or dark matter briefly becomes luminous through annihilation, or primordial gas collapses more coherently than expected, or early radiation fields transform structure formation on every scale at once. None of those possibilities is secure, yet all of them now feel less extravagant than pretending the universe is only misbehaving in one corner. The first billion years has become too crowded with synchronized exceptions, and once synchronized exceptions begin appearing across the scale from single stars to galaxy groups to the clearing of intergalactic space, the final pressure point comes into view. The question is no longer whether this or that object formed too early. The question becomes whether the accepted story begins too late, whether the universe James Webb is uncovering already carries an inheritance from conditions the standard beginning does not know how to include. The phrase "beyond the Big Bang" begins as a headline, but under the pressure of the evidence it slowly changes meaning. At first it means nothing more radical than this: the standard model that begins with the Big Bang and runs forward through the formation of the first stars does not comfortably produce what the James Webb Space Telescope appears to see. The galaxies arrive too bright, The chemistry arrives too soon. The black holes arrive too large. The clusters begin assembling too early. The ionizing photons seem too abundant for the known inventory of sources. In that first sense, beyond the Big Bang simply means beyond the explanatory reach of the usual post-Big Bang timeline. It does not imply a time before time. It does not claim that the beginning never happened. It only says that the accepted sequence from hot origin to visible structure seems to be missing steps. But the longer the anomalies remain, and the more they gather into patterns, the more the phrase begins to lean towards something less comfortable. If the early universe already looks chemically processed, structurally varied, and radiatively overactive within a few 100 million years, then the problem may not only be that the model grows galaxies too slowly, the problem may be that the model starts visible complexity from conditions that are too simple. In that case, the question shifts. It stops asking why the first galaxies form too fast and starts asking whether the universe arrives at visible history, carrying more inheritance than the standard opening allows. This is not the same as proving anything before the Big Bang. It is a quieter and more disciplined unease. Oxygen at extreme redshift means that at least one generation of massive stars has already formed, lived, and died. Strong nitrogen implies either multiple stellar generations or classes of stars so extreme that they effectively short-circuit the usual chemical clock. Dust and complex carbon-bearing molecules imply the presence of long-lived processing channels, stellar deaths, survival of grains, and mixing into new luminous systems. A protocluster with hot gas implies time for many galaxies to form and interact inside a larger gravitational environment. An overmassive black hole implies either a seed born astonishingly large or a growth history that begins earlier and runs more efficiently than ordinary paths allow. None of these observations says there is a universe before this one, but together they say something more restrained and, in some ways, more troubling. The visible universe seems to enter its own first chapter already carrying traces of previous work. That impression naturally opens the door to ideas long kept at the speculative margins. Some cosmological models imagine that the Big Bang is not an absolute beginning, but a transition, a bounce, or the latest phase in a cycle. In one class of models, the universe contracts before expanding, and some information from the contracting phase can influence what follows. In another, cosmic history unfolds in successive aeons, whose remote future and fresh beginning become mathematically linked. In still others, higher dimensional collisions or repeated cosmic births replace the picture of a singular one-time origin. For many years, these proposals remain elegant but largely untestable. They belong more to mathematical possibility than to observed astronomy. James Webb does not confirm any of them. That must remain clear. Yet it changes the atmosphere around them because it makes simplicity at the beginning harder to defend with confidence. The first visible structures no longer look like fragile prototypes slowly learning complexity. They look as if some parts of the universe begin with a head start. That head start may still be explainable entirely within post-Big Bang physics. It may come from modified dark energy, unusual stellar populations, direct collapse black holes, or classes of early luminous objects not yet properly identified. But once the data repeatedly suggests that complexity is present almost from the start, the old boundary between a clean beginning and a later accumulation begins to soften. This is where caution and speculation have to move together. There is a temptation. Once enough anomalies pile up, to leap straight from discomfort to declaration, from unexplained data to claims that the Big Bang has been disproved or that a previous universe has been detected. None of that is warranted. The expansion of space, the relic radiation of the cosmic microwave background, the early synthesis of light elements, and the broad success of the standard cosmological framework remain powerful facts. The beginning is not vanishing. The evidence does not erase it. What the evidence does is make the route outward from that beginning feel less complete than once believed. The standard timeline may still be broadly right while its first visible chapter is missing actors, missing processes, or missing background conditions that matter enormously once the Dark Ages end. This distinction is essential because it preserves both the mystery and the discipline of the mystery. The observations do not invite fantasy detached from evidence. They invite evidence-guided enlargement of what the early universe is allowed to contain. If dark stars exist, then dark matter once helps produce light and seeds later black holes. If black hole cocoons exist, then some galaxies are first seen in a pre-galactic phase centered on an already dominant compact object. If early dark energy evolves rather than staying constant, then the expansion history linking ancient light to present measurements must be rewritten in detail. If the first stars are far more massive than later ones, then chemical and radiative clocks need recalibration. If none of these specific proposals survives, then something comparably unfamiliar still has to do the work, because the anomalies do not disappear merely by being doubted. They continue to point in the same direction. Everything at the dawn of cosmic structure seems to arrive with more maturity than the reigning story anticipates. That repeated direction is what gives the current moment its unusual character. Science often advances by finding one discrepancy and folding it back into the model. Here the discrepancies do not stay one at a time. They appear in mass, in chemistry, in compactness, in black hole growth, in galaxy abundance, in clustering, in the photon budget of reionization, and in the background expansion rate of the universe itself. They emerge from different telescopes, different teams, different methods, and different redshift ranges, yet they all create the same emotional outline. The early universe looks older than it should, not older in the literal sense that its measured redshifts are wrong by some trivial amount, but older in structure, in processing, in organization, in the density of outcomes already achieved. It behaves as though more history has passed through it than the accepted account easily permits. That may ultimately reduce to missing astrophysics rather than missing prehistory. It may mean the first generation of luminous objects is radically more efficient and diverse than any local analogue suggests. It may mean direct collapse black holes and transient compact sources dominate the opening era. It may mean that the census of early galaxies is badly contaminated by unfamiliar object classes. It may mean the expansion history bends slightly enough to change the meaning of every timetable laid across the first billion years. Any of those would be significant. Yet even the most conservative versions now feel wider than the standard story once allowed. The universe no longer seems content to enter visibility as a simple fog lifting over a blank landscape. It looks more like a stage whose set pieces are already being moved into place behind the curtain. The next decade matters because this is where ambiguity either hardens into discovery or drains away into correction. James Webb still has years of life ahead of it, perhaps decades. It can revisit the most distant candidates with deeper spectroscopy. It can test the helium feature that hints at dark stars. It can resolve the gas conditions in compact red sources. It can refine the abundances of oxygen, nitrogen, and other elements in galaxies near cosmic dawn. Chandra and future X-ray missions can search for the signatures of feeding black holes in the faintest early systems. Ground-based giant telescopes, with mirrors far larger than any optical telescope before them, can take higher resolution spectra of the objects that currently sit just beyond certainty. Surveys of cosmic expansion can continue measuring whether dark energy truly evolves or whether the present hints weaken under larger data sets. In other words, the mystery is still young. This is not a closing argument. It is the strange middle phase of a scientific story in which the questions become more interesting faster than the answers arrive. That, more than any one anomaly, is what gives the James Webb era its peculiar feeling. The telescope does not simply reveal distant objects. It reveals that the first visible universe may not be narratable with the categories inherited from the later one. It reveals that beginning does not always look elementary. It reveals that darkness may have produced light in ways not yet confirmed. It reveals that black holes may precede the galaxies that seem to house them. It reveals that chemistry may run ahead of its appointed time. It reveals that the scaffolding of cosmic expansion may not be as rigid as it seemed. And once all of that is allowed to coexist, one final quiet possibility remains on the table. The universe may not be showing what lies before the Big Bang in any direct sense. It may be doing something subtler and perhaps more profound. It may be showing that the boundary between beginning and aftermath is not where the old story placed it, that the first light arrives already bearing the marks of processes whose origins sit deeper, earlier, or stranger than the model knew how to include. That is why the most distant galaxies matter so much. They are not only remote, they are diagnostic. They sit close enough to the dawn that any unexpected complexity in them becomes a message about the conditions of emergence itself. Whether that message leads to new stellar physics, new black hole pathways, new dark matter behavior, evolving dark energy, or a more radical revision of cosmic history, it points toward the same horizon. The universe at its beginning is not as blank as it once appeared. It is already busy. It is already differentiated. It is already, in some unsettling sense, underway. And because of that, the old question changes shape. It is no longer only what formed too soon after the Big Bang. It is what kind of beginning produces a universe whose first visible structures seem to arrive carrying memories of a past they should not yet have had. The deepest change may not be in the data itself, but in the posture of cosmology before the data. Before James Webb, the first billion years often feel like a narrowing corridor, a place where the broad outline is settled and only the details remain to be filled in. After James Webb, that corridor opens into something larger and less orderly. The beginning of visible cosmic history no longer looks like a smooth progression from darkness to light, from simplicity to complexity, from raw hydrogen to mature galaxies on a schedule already understood. It looks interrupted by haste, crowded with unexpected forms, marked by processes that seem to begin before their prerequisites are comfortably in place. The telescope does not prove that the standard model has failed, and it does not reveal some simple replacement waiting behind it. What it reveals is a universe that becomes more difficult to summarize the closer observation moves toward the dawn. That is the quiet force of the mystery. The farther back the light comes from, the less primitive the cosmos seems willing to be. Galaxies appear with too much structure. Chemistry appears with too much history. Black holes appear with too much mass. And the background expansion that should tie the whole story together refuses to settle into one uncontested line. Perhaps future observations will reduce the tensions, sort the object classes, and show that the first billion years are merely more efficient than expected. Perhaps they will do the opposite and widen the opening still further. For now, the early universe remains suspended between explanation and revision, between missing details and missing principles. James Webb keeps collecting photons from that uncertain border, and each one arrives from a time when the cosmos should still be becoming itself, yet somehow already seems to know more than it should.